Now RTP, or the Real-Time Transport Protocol, was originally standardized in RFC 1889. It's now 3550, although if you look at packets you really can't tell the difference, and many packets list that they are compliant with RFC 1889. The real point of RTP is to encapsulate voice or video data packets. And really what we're talking about is real-time transmissions, so this is not something that you would use for FTP or anything like that. It is for real-time data, and in particular we're talking about RTP. In just about any standardized real-time transmission, you're going to see the data, voice data, video data, encapsulated in RTP packets. It is UDP based because you don't want to wait for lost voice or video packets. You want to move right along because it can actually be disconcerting to get packets out of order or delayed. And so RTP, unlike the signaling protocols, is encapsulated in UDP. And now this shows an example of the RTP packet from the perspective of the RFC. So the top one is the actual packet structure you would see in the RFC, and the bottom here is an actual RTP packet. And you can see that obviously they're the same. I just wanted to put them side by side so that you could see, how the RFC version looks and the actual version looks. We'll be going through the fields here in just a second. Now I like to break up RTP into the first and second octets as far as the fields go, and then the rest of the fields. So the first one is very similar to the kind of things that you would see in just about any packet. There's a version, whether or not this particular one has padding. Extension is, well, maybe that's a topic for another day, but RTP is expandable, meaning that you can have lots and lots of extensions or options associated with RTP, and actually at the end of this video we'll see an example of one. Contributing source identifiers count. This means, or this is referring to, the number of different sources for the data. Often this is 0 because there's no contributing source, just the single source, but there is this option because sometimes you have voice and audio, video and audio in the same packet. So here's our second octet. The first one is a marker, or the first bit is a marker, and this just is for measuring purposes. It provides a boundary in the data stream. The second group of bits there, the payload, indicates what type of data you're actually carrying. Remember that RTP data is just hexadecimal values, and if you just said here's the data, you would have no way of determining what was actually being carried. So the payload tells us what codec was used to encapsulate this data, and in the capture you can see down there that G.729 was the codec used. Now moving on a little bit into the header, RTP is concerned with sequence numbers. We're worried about this for replay attacks and things like that. So here's an example of the sequencing. In this particular example, we can see that sequence number doesn't start at 0 or 1. It starts at some random value and then increments one by one. And not all vendors will do that the same way. We've got Polycom captures that show us Polycom does start at 1. Now next up is the timestamp. It's just the next field over, and I've just circled it here. And this gives us an indication of when the first sampling was done for this particular voice data or chunk of voice data. And the timing of this timestamp is very closely timed with the sampling rate. So you can see that the time increment between these samples is pretty standard, and that's because they're all generated from the same codec. Next up we have the synchronizing source, or the synchronization source identifier. This is the creator of this particular real-time or voice stream. This one happens to be from the G.711 source. Doesn't really matter. All of the packets from the source identify that source, and so what we can do is organize or group the packets for playback. At the bottom of this selection here we can see that the source IP address changed, and so the synchronization source identifier also has to change. Contributing source, now this is again a different packet capture because I wanted to combine audio and video, And in this particular case, we can see that these all come from 192.168.16.112, but in the same set of packets, we've got two different source identifiers, even though they came from the same guy. And that's because we have a mix. And we can see here that H.264 identifies the video codec that was used, and Siren 14, in this case, was Polycom. They didn't really tell us what it was, just a value given to us by RTP, was the audio stream. Now, you can't talk about RFC 3550 without talking a little bit about 3551, because 3551 was the first place that we started to identify and describe the codecs that would be used to encapsulate or to create the voice or video packets that would be encapsulated in RTP. So RFC 3551 provides a lot of the background and the documentation for these. They also provided, or at least initially provided, the tables that we use to describe the codecs. And here are two of the codecs pulled right out of the RFC, tables 4 and 5, from 3551. And they show on the left here the audio codecs, and then on the right we've got some of the video codecs that were identified. You can see some of our common names here. H.263 for video, G.729, G.722, and PCM-A or PCM-MU, those are G.711 versions. The RFC for RTP actually also includes RTCP, or Real-Time Transport Protocol Control Protocol. And what this is primarily used for is to provide feedback or quality of service information about the RTP stream. So you'll see RTCP packets sprinkled in throughout the stream of RTP packets, and the whole point is to provide this data. But it's important to note that the RTCP data or packets are separate from the RTP stream, so they use different identifiers, different ports, different everything, and they have their own types of messages defined that I've listed there at the bottom. One note here is that when RTP and RTCP are used together, they're supposed to use even and odd ports, although it's not always true. This is just an example of that. And then you can see at the bottom there that RTCP packets are intermixed with the RTP packets, although there aren't anywhere near as many of them. Now, the source description RTCP message is just that. It describes the connection point, provides information about the original source for the data, but again, this is different than the synchronization source ID used by RTP. And it tries to provide some way to identify in human readable format the source of this guy. That's the source description RTCP message. The sender and receiver reports provide the actual quality of service or performance data. And here we can see examples of where we're naming that this is a sender report. We got an identification for the synchronization source from the perspective of RTCP, and then we've got packet and octet counts, and then a timestamp that allows us to calculate the performance. This also happens to be what we call a compound packet, because it actually has two different RTCP packets in it. So we've got a sender report, and then at the bottom we see a source description. And so RTCP is an example of a protocol that uses compound packets. Now, for those of you that are Wireshark aficionados or use things like Wild Packets OmniPeak, you know that there's a player built in to the packet capture or analyzer software. So if I gave you a bunch of RTP packets, you could play them back as long as the software understood the codec that I was using. In the case of Wireshark, Wireshark understands G.711. So if I gave you a series of packets encoded with G.711, you could play it back right inside Wireshark. Pretty cool. So RTP is very vulnerable to eavesdropping. Well, what can you do about that? You can encrypt the data, which means that Wireshark couldn't play it back. You could also obscure the codec. You could hide the value. You could use one of the RTP dynamic types, kind of like Polycom does, and not advertise what codec you're using. That also makes it difficult to play it back. RTP and RTCP both have extensions. SRTP and SRTCP are the secure versions. And the whole point is to authenticate part of the packet and then encrypt the data portion. And so these are what we call extensions to RTCP and RTP because they just expand the header and add extra functionality.